So let's run through the example one by one. 6.1 is the 2 to the 3 factorial design, and you have money, so you do it twice. And when you do it twice, of course, you can code them, and then here is the sum of the two repetitions, and you can build the right wall, left wall, and then get the computation out. Okay, and then rather than solve it that way, and we're going to solve it this way. The same old tricks. The intercept, and then the main effect, and this time we have the two blocks. Okay, block 1 and block 2. I'm sorry, 2 repetition, not 2 blocks. And in the exam, be careful. Okay, I will make that very, very clear. This is repetition, or this is a block. Okay, and can we have repetition within block? Can we? So can I have, one block, I can do it twice, and another block, I can do it twice. Is that possible? Of course, right? So just be careful. Blocking is due to economics. No money, no time, right? Repetition is I have time, I have money, I can do it. So sometimes I say that, I have enough money, I have enough time to do twice within one block, and then next year is another block, I do it twice. So, so every example is your job to read through them, and remember you can do it 2 different ways, right? One is the sum, find the effect way. And the other way is the way I'm basically doing the same things, but this time X transpose to this, and then calculate the X transpose X inverse, and then you'll find all the parameters. Okay? And I already give you all the spreadsheet needed, and then you will get the effect and convert them into sum of square. And whatever, just like before, you do it using the regression approach, or you're using the sum, balance, add them up together, you should get the same answer. If you don't get the same answer, something is fishy. And the other thing is that since we're doing this in an orthogonal way, so you know that you can double check that the sum of each one of the contrasts should equal to 0, the multiplication of A times B, A times C, A, B, C should equal to 0. And since we're using the contrast approach, you should have the X transpose X and X transpose X inverse diagonal matrices. Okay, so this is example 6.1. Do it twice because you have money. So you have 2 replica. Okay? And 6.2 is the example that you have A, B, C, D, 16 of them, but you have enough money to do it 1 time. So you only have 1 trials. And because you only have 1 trial, remember we did that smiley face approach and find the main effects and everything. Now we'll do it again, but this time no smiley face, we just use our old regression approach. So when I say regression approach, means what? You have the main effect, and you have the 2-way, 3-way interactions, and X transpose X, X transpose x inverse. And people pay attention here. How come I only have AC, AD, no BC, BD? Remember when we did the smiley face, we supposed to have what? 4 main factor, 6 two-way interaction, 4 three-way interactions, and so on. But since I already know that based on a smiley face, I only care about those terms. So when I run this, I can say that, hey, I don't care anything, I only care about those terms I want to use. And you know what will happen to the rest. The rest will be all combo together, becomes the error term, right? Yeah, so if, okay, you said that, Simon, I don't trust you. How do I know you give me the right spreadsheet? And one way you can do it is what? Pull them all the way there, start doing your AB, AC, AD, BC, BD, 6 two-way interaction, have every terms, and then you will have a large, very large X transpose X, but when you decompose them, you end up with A, B, C, D, A, B, A, D, and then you can say that, oh, I only care about those terms, so I'll keep the sum of square named. A sum of square, B sum of square, C sum of square, AC, and the rest of those, lump them together, become your sum of square, your error terms. You follow me? So I did the cheap way here, but in reality, just you have a pizza, right? You say, hey, A, you can have a slice, C, you can have a slice, D, you can have a slice. The rest, nobody touch. Put them together, we call them sum of square for error term. And we're doing that smiley face in this way. So, again, when you look at them, okay, either way, you should end up the same answer. Okay, sum of square is sum of square. You look at it from a regression line approach, from the central station, the contrast approach, no matter what, that's the total amount of scatteredness there for you to summarize. Sum of square cannot, law of conservation. You cannot generate sum of square, you cannot reduce sum of square, you can only partition sum of square. Okay? That sounds very philosophical. I like it. Okay, 6.6. 6.6 is just say that, I can have the quadratic term by doing repetitions, adding terms in the middle. And right now, the notes only tell you, here's the way to do it. I'm just trying to show you that you can do it in a regression way. What you're going to end up doing is just having your A term, B term, and so you will have this with the repetitions. That's something I forgot. People, think about it. Okay, we know that if I have an A term on the positive side, A term on the negative side, I have a B term on the positive side, on the negative side. Okay? Now I'm saying that, so I have low A, high A, low B, high B. But then I add a bunch of repetition, 5 repetition in the middle. Okay? So I have -1, +1, -1, +1. So I have negative, positive, negative, positive for the 4 corner, right? So we code them such a way. How are you going to code the center term? You need to code them as what? 0, 0, 0, 0. Does that make sense to you? Right? That's the positive side. Well, that's the negative side. This is the positive side. That's the negative side. That's the positive side. I'm standing in the middle in the room, right? what will be the code for the middle of the room? I said, oh, I would like to have some repetition in the middle. Should be 0, 0, right? And that's the only things I would like you to pay attention to is the coding here, why it's 0, 0. Okay? And then you'll end up with the partition of the sum of square and 2.4 A term, B term, C term, and you'll get exactly the same things here. Okay? So this is kind of like repeat what we've done, but this time I want you to not just do it. You have these things in mind. Okay? The big picture. Next. Let's introduce the blocking. Okay? And let me use this part. Okay, so this time I said that I have money, so I do 3 blocks for this 4 2x2. So I have the 2x2, 2x2, 2x2 for 3 blocks. Okay? One thing that's important here. People, within every block, I have a complete permutation of everything, right? So is there any confounding effect between blocking and any of my A effect, B effect, or AB interactions? You follow my questions? Remember last time I said that, I don't have enough money, I don't have enough time, so I have a complete experiment. I break them into, first half, second half, this wall, that wall. Basically, chop the entire things into 2 pieces. So I will have some blocking effect confounded with some experimental effect. But in this case, do I have that problem? No, right? Because actually I have enough monies. So within every block, I have enough money to run a complete cycle, okay, of everything. And, for example, what if I said every block I have enough money to run this twice, so I can have repetitions 1 and repetition 2. So rather than have A observation, I have 4 observation, I have 8 observation. Same things. That means what? Hey, block is block, effect is effect. You have enough money to have the duplications and everything, okay? What is really dirty is, I'll show you 1 or 2 examples later, is, what if I only have money to run 1.5 block? You guys follow me? I finish this 4, and I say, hey, you can do 2 more. And they have another money here and said, oh, you can do another 2 more. So now you're running an experiment like very unbalanced, and how to deal with that. I'll show you the example, but the unbalanced computation is going to make you dizzy if I try to do it in Excel. And how we're going to do that, we'll let SAS to deal with that kind of very uneven situations, okay? But everybody sees that if I can run a complete, manifest everything I can run, there's no such things as confounded here. Okay, so 7.1, no confounded. Let's run 7.1, 7.1. Okay, so 3 blocks, 1 block, 2 blocks, 3 blocks. Okay, so now you have your blocking effect. And one way you can look at this is the blocking effect, look at the code. Repeated with anything else? No. So in other words, this contrast never happened anywhere else, right? So there's no confounding. Here, let me ask you this. Remember we have this one before? A, B, C, D, and then let's just say I had using A, B, C, D as my way to do it, and then I have a blocking effect here. If, okay, the code, whatever I have here, A, B, C, D is used as my separation exactly as the same as here. That means what? Your blocking effect and your A, B, C, D are confounded. You follow me? So one way, sometimes people call it aliasing. What is alias? You know, James Bond is 007. So when you talk about James Bond, you talk about 007. Same guy. So A, B, C, D and blocking is 007 and James Bond. Then they're the same guy. You cannot separate the two. That means confounded. Okay? And in this case, the 7-1. Let me clean this one. I don't need it anymore. Oh, here. Since there's no confounding, I can calculate that, and you can have your blocking effect and main effect. So intercept here, and is X transpose X, and X transpose X inverse, X transpose Y. Break them down into your ANOVA table. Okay? And your ANOVA table, sum of square, 208, 75, 833. The effect is here, 833, 75, here, 208, 75, 833, sum of square. Exactly the same things. Okay? And for any of you feel like always want to ask me, can you give me cheat sheet or something for the preparation for exam? I would say the best exercise you should have is run every example, do it the sum of square way using the contrast. In other words, is that can you repeat this using the textbooks or the handout I give you? Can you do it in a regression way? If you do it two different ways, you end up with the same answer, you got it. But if you just couldn't piece them together, that means something is missing, and the devil is in the detail. You need to go back and double check, where did I miss? Okay? And if you cannot get that done in your next homework, I'll give you the homework due, like I promised, next Thursday, because I need to give TA some time to finish the grading of the work I already give. But when you've done your part, don't just copy paste. You need to think about, hey, for every example, can I do it more than one way and get this to the same answer? If this partition, you end up with different things, and you couldn't figure out the degrees of freedom, okay, then you're in troubles, okay? We have 3 blocks, so the degrees of freedom is 3 minus 1 is 2. We have A effect, positive or negative. So 2 minus 1, 2 minus 1. And AB effect interaction is 2 minus 1 times 2 minus 1 is still 1. Okay? And so totally 2, 1, 1, 5, and totally 12 observation minus 5, you get your error term, 6 degrees of freedom. Okay? Next, 7.2. 7.2, this is the one we should have confounding or no confounding. Come on.
That one should have confounding.
Yes. Why we have confounding?
Because the two blocks aren't the same.
That's a smart answer. But what I'm trying to say is that totally how many observations I need? 16, right? But do I have enough to run at least 16 per block? No. So obviously I need to split them. The minute you split them, you have your confounding effects you need to study. So here, block and A, B, C, D, they're confounded. Or you can say that the blocking effect and A, B, C, D, they're aliasing. When I'm talking about block effect or I talk about A, B, C, D effect, I'm talking about the same things. When I talk about James Bond or I'm talking about 007, I'm talking about the same things. So here are all the terms needed. And 7.2. Okay. Block 1 and block 2. Okay. And you can think about it this way, okay? Since we're using block as my, watch here. Block is positive 1, negative 1, and what is my ABCD effect? Okay? I didn't do it, but here. If I have a times B times C times D somewhere, let me say, put it here, A, B, C, D, okay? And then I'll have a product of this 4. Okay. Okay. Now, look at the A, B, C, D and the blocking effect. Can you see they are alias? Can you see James Bond and 007, same person? At least based on the code. Right? Yeah. So this is the tricky part that, or the price we pay for doing that. And for those of you who missed the class last week, on Monday, remember, because of this, usually, what is the game rule? We're using high interaction term as our blocking effect, or low interaction, many effect, or low interaction term as our blocking, usually. Huh? If I give you the choice, using many effect, A effect, B effect, to separate the two block, or two-way interaction, or using a five-way interaction to separate the two blocks, which one usually should be the case? The high-level interaction term, right? Because I explained the last before. Why? Because usually people have difficulty to explain three things or four things interact together. That's one. And the other thing is that usually, logically, in our investigation, you start from the low level, A effect, B effect, you explain those things you can explain first, and then you gradually talk about the high level interaction term. Okay? This is very, kind of like incremental in our logics. Anyhow, if you do this, you can still have your X transpose X inverse, X transpose Y, and end up with your sum of square computations. And you compare those computations, sum of square was your sum of square here, okay? And there should be the same. And for me, things I check is the two biggie. A effects 1870. A effects 1870. And the blocking effects is the lump is 13A7. and the blocking effect is 1387. Okay, then, if for matrix computations, I have those two big number in the right place, I'm probably okay, not doing anything wrong, okay? I did some things. When I worked for airlines 30 some years ago, typhoon hit Taipei. I have two 747 waiting to get loaded to San Francisco. And a lot of time I have all the big cargoes, and all I need to do is just look at it, 10,000 pounds here and 8,000 pounds in the back. If the big one, I got it right, okay, I probably will say, okay, this is head heavy. I need to add a little bit to the tail to keep the attack angle, the trim line within 4 degrees. So even though, this is old days, I need VAX for major, big computer to do the computation. But I just look at it and said that, okay, where's my center of mass? And my tail should be a little more than my head. And if I got a too big number right, most likely my computation is not way off, okay? This is, I think I said it. I haven't seen anybody said it before. For system engineer, I would rather be roughly right, not precisely wrong. So if I see the number, okay, this is about right. I know the captain not gonna yell at me later because I will get a computation right, okay? So anyhow, you can compare your regression approach versus your blocking effect and get all the numbers compare. One thing I would argue here, okay, while you're doing the ABCD computations and blocking effect, I'm a little nervous here. You guys know why? I really prefer my blocking effect small. This number is quite big. And that to me is kind of like, I better double check, make sure there's nothing fishy going on, okay? Okay, but again, you can check the p-value, the f-test with the degrees of freedom and everything's here, okay? They did not check the blocking effect. People, if I want to check the blocking effect, do you think it will be significant or not significant? The ABCD interaction term, based on this. Based on a sum of square?
It should be significant.
It should be significant, okay? The only thing is that, so what I'm saying, statistically, numerically, that ABCD James Bond is significant. But the only reason we didn't investigate that because this is the things we care, okay? James Bond, we already said it's alias. We don't care. We just say that, hey, that piece we take advantage of that to save our life, to make our experiment here. What I'm saying is, this are the things we want to investigate. This piece is kind of like, it's a sacrifice piece. We took it out, even though the sacrifice piece is quite big here, okay? And so when I said I'm a little bit edgy here is that, I'll say, man, I sacrificed quite a big piece. That's the part I don't like. You guys follow me? But if you say that economically or experimental design-wise, did I do the job? I did the jobs. I get my ANOVA table. I have all the significant investigated. Okay? And one thing's, it's not emphasized here. A lot of time in human factor type of experiment, and for example, remember I talked about two different surveyor, one male, one female, or a lot of time two coach or something. And at the end, oops, too quick. At the end, you will say that, oh, those who under coach ABC, Jiang Do, and those coach under coach Jen Do, okay? The training mechanism are the same, but they just one trained by one coach, one trained by the other coach. If you ask me, are there going to be coaching style differences between the two? I'll say definitely, okay? But coaching effect is not an effect we want to investigate. What we care about is what are the dosage of A, B, C, D, or those things, okay? So, next, this is a good one. This, guess what we did? This time I don't have enough money to run all 8 in one shot, right? So what I did is I need to do block. So I have block, but you know what? I have enough money to do full block. So I can have, this is one, and here is another one, okay? The only difference is what? I said that, can I do it this way? On the first replicant, I use ABC as my separation. And this one, I'm using AB as my separation. Can I do that? Of course I can, right? Just different sequence. So because of that, see here, because I'm using ABC, so you can tell on this block here. Let me show you a little more. I just use, not that. Okay, let me use this page. Okay, so watch this. -1. 4 of them. They start from positive or negative. I don't remember. Doesn't matter. Okay. And then, of course, okay, so here are the complete design, right? And then, so first time I'm using ABC as my separation. So I will have product of these 3 guys. Boom, done. And then I'll say, hey, data sort. Yeah. Using ABC, give me 1 block and another block. And you can tell here, low, so 1 is in 1 block. And this one is what? A is high, B is high, C is low, so I have AB. And then this is AC, and this one is BC. Agree? And 1 block. And of course, here will be ABC, and here will be A, here will be B, here will be B, and here will be C. So here is the name. Let me just call it OBS, observation. Okay, and then let me use general here. No. Well, you guys know what I mean. This is really is That's simple, but they always, yeah. Text, where is text? There we go. Okay, so here I'm using ABC. I'll end up look like this, right? And then all I need to do is what? Copy paste. Hey, I don't want it. I have another repetition I can do, but this time I don't want to use ABC. I want to use BC. I want to use AB as the block. Okay? And usually it's what? ABC, I don't care, sacrifice. Now let's just say AB, I don't care, sacrifice. Okay? If I sacrifice AB, that means what? Do they sacrifice AB? Yeah, they sacrifice AB. So it should be A times B, right? And if it's A times B, and all I need to do is say, okay, hey, give me another sorting of this using AB. So expand, store based on AB. Okay, so now you can tell this is AC, BC, AB in one block, AC, BC, AB in one block, and then one CAB in another block. You guys see that? Okay? And let's just say, hypothetically, I want to torture you in the exam. Can I have a 16 trial experiment, and then every time I'm using different thing to generate a block? That'll be just, nonsense, right? Labor intensive, but it's doable, right? You guys follow me? Repetition, every time I'm just using different thing as my block. Okay? I said do it in an exam, it's nonsense, right? It's labor intensive for no reason. But in the real world, why do you think people want to do that? Because every time you're using something to confound, you sacrifice that, right? So it's kind of like 007, sacrifice 006, sacrifice 005, sacrifice. We don't want to sacrifice the same guys every time. We kind of equal opportunity, sharing all the nonsense together. Okay, that's the reason. So when you do the computation, here is the way you do it, and then you'll have the effect calculated. And so here is the repetition 1, repetition 2, and you can have your X transpose X, your main effect calculated. Okay. Next, let's move to.
Quick question. Why does the blocks within replicants have 2 degrees of freedom?
Say. Oh.
Yeah, that has 2 degrees of freedom.
Why?
There are only 2 blocks within the replicants, right?
Right. Yeah.
And then we have 4 blocks total.
No. Replica got 1 degree of freedom, agree, right?
Yes.
Okay? Now, if, okay? Well, let's actually, the easiest way to think about this is using what I just did. Oh, no. Okay. See here? 1 block, another block, okay? We randomize this guy, right? Mm-hmm. Okay? If I'm using the same things over here, okay, then it's 2 minus 1 times 2 minus 1. But here, it becomes what? Here, logically, do I have the freedom to to separate them within every replicant. Here, this is one side. Here is on the other side. So the contrast is this way. This, I'm not repeating the same thing. This time is this contrast against this contrast. So it's a new vector, a new comparison. Agree? So I'm using this here. Every contrast you can consider as what? As an equation, right? Because the equation here is what? This 4 minus this 4, right? This time is this 4 minus this 4. So every time when you come up with a new contrast, you lose 1 degree of freedom.
Okay.
No, you say okay, but let me confuse you a little more. So you will figure it out. Remember, I said it before. I have, say, 30 students in the classroom. So if I want to know your height, say your age, before I ask your age, free, right? So I have 30 degrees of freedom in this classroom. But the minute I said that the total of the age together is 244 or 2440, or I said the average age of this 30 student is 22.3. Is that an equation? Sum of x1, x2, x3 equal divided by 30 equal to a number, right? So whenever I write a equation, that equation basically took away 1 degree of freedom if it's independent or orthogonal. So here, did you see that I have one equation saying that, oh, I can build a contrast using this 4 against this 4. And then, did I repeat the same equation? I'm using a new equation. So whenever you write a new equation, okay? Whenever you write a new equation, you lose 1 degree of freedom.
Right, so we started with 4 because there were four blocks within the replicants, and then we wrote 2 equations. So we subtract 2 and have 2. I got it.
Yeah. Okay. So, confusing enough?
Yeah.
Okay, good. And you guys are not necessarily going to take my Bayesian class. A lot of time in my Bayesian class, I will even say this. We're talking about eigenvalue or eigenvectors, the same things. There are a bunch of observations, random dots in the space. The minute I said that all those dots can be organized by 2 vector or 3 vector, the minute I start using those vector, I start summarize things using a line to represent or vector to represent that. The more vector I have, the less degrees of freedom left for them to be scattered around. And so a lot of time it's always, I call it system engineering intelligence. Is always try to do what? Using few equations to summarize tons of stuff. Then that means you find a really nice equation. Okay, so if you do it this way, you can this time you can turn them into 4 blocks. It was so repetition 1, repetition 2, and the key things I need you to pay attention here is there are 4 blocks, and there are only 2 replicants. Okay, and so when you do the computations, there are repetitions, sum of square. There are blocks, sum of square. Okay, next. No. Next one, move to this one. Okay, so now we're really start doing the cheap stuff now. We're saying that, hey, it's science fiction. You have that kind of money. Usually what we have is the opposite. You want to do a lot of stuff, but you don't have a lot of money. So you want to do it the cheap way. And so we're going to do a fractional factorial design. And what is fractional factorial design is rather than having repetitions, do it again and again, I'm saying that no, 50% discount. 75% discount. You can only run half of it. You can only run 1/3 of it. Okay? So when you run that, like this way, I'll come back explain what's resolutions, okay? But first, I prefer you play with it than worry too much on the terms. But here, okay, we're having the A, B, C, D as my, so if I have 4 factorial for A, B, C, D, should be 2 to the 4, 16 trials, right? But how many trials do I allow? Nope, only half of it, 8, okay? So you run the 8 trials here, and here is the 8 trials. Half of the 8 trials, okay, A, B, C, D. First thing first, how come I don't have a blocking effect anymore? How come I don't have the blocking effect anymore? Young man, remember, I told you guys, to have replicate as an effect, I need to have replicate 1 against replicate 2. If I want to talk about blocking effect, I have to have block 1 against block 2. Now do I have 2 blocks to build the contrast, or I only have 1 block? If I only have one block, I don't have a second block. Remember? Totally, I'm supposed to have 16 observations, but I only say that, hey, you only allowed to have half of it, 8 observations. Then do you have block 1 against block 2? No, because there's nothing to against, right? I'm only looking at things from a partial view. So that's why it's called fractional factorial design. And then when you run a fractional factorial design, okay, and you still can do your observations and your regressions the same way, X transpose X. Okay, now, before we get into the computation here, I want to start talking about the resolutions and the effect here. Let me find a new clean sheet. Okay, so A, B, C, D. Okay, and I have to run this. Oh, I'll do it. -1, Control C, 1, 2, 3, 4. Yep. 1. Done. Okay. 4 negative, 4 positive. Two negative, 2 positive. 1 negative, 1 positive. Okay. You guys will do the naming, okay? But watch here. If I'm using A, B, C, D as my way to block things, okay? So, product, okay. And then I said, hey, I'm using A, B, C, D to separate the two blocks. Data store. That was quick. Okay. And people, can I say that I'm only using the positive one block? Is that okay? Okay. Or I can say I'm going to only do the negative block. Okay. So I'm only allow you to run half of it. Okay? And when you only run half of it, guess what will happen here is, watch, okay? If let me start from the A term, okay? The A term is here. Let's just do the A term first. Okay, A term times A, B, C, D become A squared B, C, D, right? And if the A squared B, C, D square, positive 1 square and negative 1 square, the same things. So I will end up with B, C, D. So watch this. If I do a product of B, C, D, do you guys see any problems here? B, C, D, and A, are they the same? You see that? So in other words, is that the minute you're using half of the block, say A, B, C, D doing the blocking, so you know that A and B, C, D, can you tell the difference between A and B, C, D? You can't. So, same things, okay? B manifests gonna confound it with what? With ACD, right? So let's try ACD. ACD. And I hate that because let me try something ABC. Okay, let's say we try D effect. D effect gonna confound it with which one? ABC. So let's just do ABC. BC. So, product of A times B times C. Okay? And can you tell? The A, B, C, and D exactly the same. That is the equations, okay? They're trying to say here is that D effect and ABC gonna be the same. So here's the challenge part. So in reality, can you tell the difference between I'm investigating D effect or ABC effect if I'm only using half of the block? You can't. So you're saying D effect and ABC are gonna be aliased. Okay? Or you can say that the other stuff for the same reason. But people, if I said, hey, there's an effect here, could be D, could be ABC. Which one you think you probably, your boss would like to know, consider? You found an effect, could be D man effect, or could be ABC three-way interactions. Which one, say it's significant. which way you think will be better explanation or worth the effort to explain it? To explain it as a D-man-effect or explain it as three-way interaction ABC? Usually we will say that, statistically they're the same things, but we will keep it for the main effect. Okay? So, let me, last time I did it, right, I can block this using two confounding, and so separate them into different blocks. So there's a name for these things, okay? And this is not going to be in the exam, but it could be in your job interview. People call these things resolutions, okay? And what's resolutions, okay? Who defined it? I don't know, in the 1950s, right after Second World War, I think so. Okay? And there's a logic behind all those things, but to you need to just remember this, okay? Resolution 3 and resolution 4 and resolution 5 usually are the three resolutions we deal with. For resolution 3, these are designed in which no main effect are alias with any other main effect. Here, in our example, I just showed you, main effects, A will be alias with BCD, B will alias with ACD, C will alias with ABD, D will alias with ABC. So all the main effect alias with three-way interaction, not two-way interactions, not any main effect. Agree? So this is good because we keep the main effect clear. And then they said that, however, okay, it could happen is that your main effect alias was your two-way interactions, and two-way interaction alias with each other. Okay, resolution 4. Okay, no main effect alias with any main effect with any two-way interactions, but two-way interactions are alias with each other. This is alias 4. This is resolution 4. And finally, resolution 5. These are designed, no main effect or two-way interactions is alias with each other. Main effect or two factor interactions, but two-way interactions are alias with three-way interactions. Okay? And those terms, you can have a cheat sheet somewhere, but the principle for me is very simple. The most precious things is what? My main effect. So I would like to keep my main effect if they have to alias with something really, really high level. And if I want to talk about my two-way interactions, I want to keep my two-way interaction clean. If they have to alias with something at a high level. In other words, is that I'll keep my main effect as clean as possible. I will keep my two-way interaction as clean as possible. Okay? Because those things are easier for me to elaborate. Okay? And that's the purpose of this, okay? And they show you that how they come up with or the projections for those terms. But for me, be honest with you, no need to memorize it, okay? Just by principle, you know that main effect, two-way interaction, low level interactions are the holy grail. I would like to keep as clean as possible. You want to muddy with something, muddy with the high level, 3, 4, 5 level interaction terms. Okay? And when you run the experiment here, this is the first one. Okay? And you can end up with all the parameter using the contrast. And next, here is the 16 trial experiment, and this time I'm using E alias with ABCD. Okay, and so this is example 2. Okay, A alias was ABCD, and then you find your sum of square. Okay, and next. There we go. There are, in the lecture notes I copy, there are some multiple comparison and some fixed effect stuff. I will talk about those things later altogether, because those things are very mechanically boring. I would rather summarize them in one lecture, so you will see. Basically, you can think with me rather than just repeat the same things again and again. Okay? And in A3, we're running 1/4 of the experiment. And before we run a 1/4 of the experiment, here is the things they try to show you. Okay, people, think about it this way, okay? Say I'm using ABCE as my separations. I'm also using BCDF. So I'm using two main effect to do the separations. And when you do that, okay, if I'm using ABCE, I'm using BCDF. Okay? YADEF also will be confounded in the block. Because, watch here, ABCE times BCDF. B will be square, right? C will be square, right? And DEF not going to be square, right? That's why you block and block, okay? And then you will have this casualty because of those two blocks. And now, if I have a resolution 4 here, say I'm blocking ACE, BCE, okay? And you can tell this times this times this, I'll end up DEF get blocked also. Agree? And let's try another one, just for fun. Okay? If I have A, C, D, F, and I have B, C, F, G as my two separating blocks. What else will get blocked?
A, B, D, G.
A, B, D, G, exactly. Because C and F both get squared out. Okay? Now, what if I have another block? It's called which one I want to use? I just say I have a block called B, main effect. Then you need to think about this. Okay? This 2 casualty will be what? C, F, G, right? And this 2 is A, B, C, D, F. So all you care about is the minute you start building the blocks, okay, I say, hey, I want to have this effects, this effects, this effects. Any 3 of them, you need to not only think about what the contrast they're going to cause, also any 2 of them will causing a collateral damage somewhere else. You follow me? Okay. And as such, yeah?
Yeah, 5.
Oh, okay. I lost my recording last time again. So here are some cheat sheet. That's why I call it cheat sheet. Is people shows that, hey, when you block something, what else will be blocked at the same time? Okay, and there's a whole list of them, and you can actually, if you go online, just say that experimental design resolutions. They will show you a list like this. Okay, and don't need to memorize this. I'm just saying that here's the cheat sheet. People will use and say, oh, I'm blocked this, I'm blocked this. Immediately you will look, what else will get blocked at the same time. Okay. I will give you one bigger homework due Thursday, and mainly to deal with some of the contrast here. And the other thing is, please get access to SAS. Unless you said that, I don't care, I'll come to this room, do my SAS homework. Okay, we have SAS here and downstairs 154. But if you want to, have your own SAS legally, you can download it and put it on your own computer. Or there's another way, I think, you can double check. At least when I taught the reliability, Mosaic's supposed to put SAS on VPN, okay? But SAS is free, so download that. Okay, see you next time.